Let's go ahead and look at this example problem, which is example number 5 out of that packet. Okay, so this is the same deal. It's a beam now. It has a concentrated load at point B, has a uniformly distributed load acting over the entire length, and it's simply supported with a simple support at the left end and a simple support at the right end. Excuse me. So let me go through and work out this problem. Let me assume too that you guys can solve for the beam reactions. So at the left end of this beam, you would have a reaction force of 54 kips, and at the right end, you would have a reaction force of 49.20 kips. So I wrote the wrong damn number. 49.20. This is 54.0 kips. All right. So let's assume that you guys can do that. All right. Now, like I said, I like to put in some construction lines in here so that I can draw my shear force and bending moment diagrams with a bit of precision. It doesn't have to be perfect, but if you just go put a little bit of effort in, it makes it a whole lot nicer. So I'm going to work left to right. Always work left to right, never work right to left, always work left to right. So I'm going to work off the left end of the beam. The shear to the left of that support is equal to 0. So I could say that the shear to the left of point A, so V sub A minus, that's the shear to the left of point A, is equal to 0. All right, I know that the shear to the right of point A, VA plus, that's the shear to the right of point A, is equal to the shear just to the left of point A plus the change in shear that we get at point A. So the shear to the left of point A was 0. The change in shear that we get is equal to the magnitude of the applied load. That load goes upwards with a magnitude of 54 kips. So that means the shear to the right of point A is equal to plus 54 kips. So I'll just say that that's about that point right there. Okay, so go in and sketch that line, and I can put a number here. I don't have to label the units because the units are labeled over there on that axis. All right, questions? I'm watching the chat window over here to my left. That's why I keep looking over this way. All right, now let's see. I'm going to stop. I'm going to go between points A and points B because there's a constant load and then there's concentrated force here. That force represents if we were mathematicians, it would be a pole, right? Can't integrate across a pole. So I'm going to go to point B. I'm going to say that the shear just to the left of point B is equal to the shear just to the right of point A plus the change in shear between points A and B. So that's equal to 54 kips plus the change in shear between points A and B is equal to the area under the load curve between those 2 points. So this is an area, and that is equal to the change in shear between points A and B. So what is the area of that? It's a rectangle, so it's just the base times the height. The base is 12 feet. The height of that rectangle is 2.64 kips per foot, but the load points downwards, so it gets a negative sign. So when we do that, we get, let's see, 12 into 2.64 gives me minus 31.68 kips. So if we take 54 plus 31.68, that gives us a positive 22.32 kips. So we go from 54 there using an approximate scale. That's going to be about 22.32 there. So go ahead and label that 22.32. I'll use my straight edge and sketch that line. All right. Okay. Now at point B, we have a concentrated force acting. So we could say that the shear force to the right of point B is equal to the shear force to the left of point B plus the change in shear at point B. So that's equal to 22.32 kips plus the change in shear is equal to the magnitude of the load. It's acting downward, so it's a negative 24 kips. So that means that the shear force just to the right of point B is equal to, let's see, minus 1.68 kips. So it's just below that axis, minus 1.68. Like that. Okay, that change in shear is instantaneous like that. Okay. Now, we go down here, so we can say that the shear force just to the left of point C is equal to the shear force just to the right of point B plus the change in shear between B and C. Change in shear between B and C is equal to the area in this rectangle here. So that's delta V BC like that. Okay, let me scroll down just a little bit. So this is equal to minus 1.68 kip feet. No, kips. Plus the change in shear is going to be equal to 18 feet times a minus 2.64 kips. So when we work out that math, we end up with a minus 49.20 kips. So right about there, minus 49.2. And if we use a straight edge, there we go, not terrible. All right, I need a little bit more space here. So let's see, I can do this. Whoa. Try that again. There we go, perfect. Okay, and so then finally we could say that the shear just to the right of point C is equal to the shear to the left of point C plus the change in shear at point C, so that's equal to minus 49.2 kips plus the magnitude of this force, 49.2 kips, and that's equal to 0. So we go back to 0 there, and we would say that our shear force diagram closes. So again, if the shear force diagram doesn't close, then you've made a mistake either in solving for your reactions or you made a mistake in drawing the shear force diagram. All right, questions? All right, then let's go ahead and sketch the bending moment diagram. Give myself a little bit more space. All right, so I'm going to draw these green construction lines in again. Like that, and there we go. All right, now the bending moment diagram is going to, the bending moment is 0 because we have a pinned end there, we have a pinned end there, the bending moment is 0 to both those places. So this is point B here. So we know that the bending moment diagram at A is equal to 0. We know that the bending moment at point B is equal to the moment at point A plus the change in moment between points A and B. So this is equal to 0, and then the change in moment between those 2 points is equal to this area under the shear force diagram. I did not mean to do that. So calculate that area there. So that is the change in moment between points A and B. So if we go down here, that's going to be not red. Plus, what I'm going to do is take the average of the force to the left and to the right. So I have 54 to the left. On the left end up here, I have 22.32 there. So 54 plus 22.32 there. So those are units of kips. And then I have a dimension of 12 feet there. And so what I end up with is a moment of 457.9 units of kip feet. So I'll call that point right about there. I'll say that's 457.9 kip feet. Now, in order to get from the shear force diagram, which is linear, down to our bending moment diagram, I have to integrate. So I'm going to integrate a first order curve in the shear to get to the bending moment. So if I integrate a first order curve, it has to be second order curve. So my bending moment diagram is a second order curve, and it could either look like that. That was pretty bad. Let me do that again. It could either look like that or it could look like that. Now, which one of those two is correct? And how do I know? Okay, well, the answer is that the magnitude of the shear represents the slope of the bending moment diagram. So over here at the left end of that segment, at point A, I have a slope that's 54. So if that's 54, it goes like that. If I have a slope over here at the right end that's equal to 22.32, then that slope is shallower like that. So I have to have a second order curve that fits with those slopes. So that means that the first curve that I've drawn here, this is the right one. This other one is incorrect because it doesn't match the slope at the left end and the right end. Okay, now Max asks the question, the shear forces would only be the forces acting directly downwards. Well, all of these forces that are up here on the beam are actually external loads. We have an externally applied force of 24 kips. We have the distributed load of 2.64 kips per foot. We have a reaction force at A of 54, a reaction force at C of 49. None of those are shear forces, though. All of those forces affect the shear force, but none of those are actually shear forces. If we wanted to see the shear force, then what we would have to do is cut a section in the beam. Let me do that. I'll go down to the bottom of the page, okay, like this. So if we wanted to see the shear force, then what we would do is this. So here's the beam, top flange, here's the bottom flange. I would come in with a cut section like that. And here's the the opposite end of the beam, cut section. So the shear force would be this. That would be the shear force on the left-hand section. That would be the shear force on the right-hand section. So that is a shear force V. And if you're looking at the diagram at the top of this page, you can't see that shear force. The external loads affect the shear force, but the shear force itself is an internal thing. It's like the axial force in a truss member. Only time you see the internal axial force is when you break the member, right? You cut a truss member and you draw the internal axial force. That's when you see P. Same thing here. That's the internal shear force. If we went on one step further, we could say that that's the bending moment M, and that's the bending moment M. So this moment is equal to that moment, just in opposite sense because they're drawn on opposite sides of the cut. This shear force is equal to that shear force, just in opposite sense because they're drawn on opposite sides of the cut. Right? So maybe I'll come back and do a check at the end of this example. But so none of those forces are shear forces themselves, but they all affect the shear force in the beam. So this diagram right here is the shear force diagram. That is a plot of the internal force V over the length of the beam. All right, let's wrap up the bending moment diagram then. So I'll scroll down here. I wish I had a little bit more space to work, but I could say that the moment at point C, drawn in blue, of course, the moment at point C is equal to the moment at point B plus the change in moment between points B and C. So this is equal to 457.9 kip feet plus the change in moment. And that change in moment is equal to this here. This is an area under the shear force diagram. It's not zero there, but it's close to zero. So that is the change in moment between points B and C, delta M sub BC. So I can go over here and I could say that that's equal to the average of the forces. So at the left end, we have minus 1.68 plus a negative. At the right end, we have a minus 49.20. And then we multiply by the length, 18 feet, and what you end up with is 0. So over here at the right end, we end up at 0 again. Okay, the slope of this curve, oops. The slope of this curve at the left end is equal to minus 1.68. So the slope is like that there. Over here at the right, it's equal to minus 49. So the slope at that point is like that. We integrate this, which is a first order curve, and we get to the bending moment, which is a second order curve. So we have a bending moment diagram that is parabolic. It either looks like that or looks like that. How do we know which one is correct? We know that the second one that I drew is correct because it matches the slope up here at the right end. At the left end, it matches the slope down here at the right end. So that's got to be the right one. So we'll erase that. And then we'll go in here and we'll label this as a kink. So there's a kink in the bending moment diagram. It's continuous at that point, but it's not smooth. The external force of 24 kips acting at point B causes a kink in that bending moment diagram.